Well, I'm Víctor Duro, and today I'm going to be talking about this work that, together with my advisors, we've been developing this last year in the framework of my thesis, which is entitled Enhancing Turbulent Flow Control via Data Fusion. So it's obviously related to the complex problem of controlling turbulent flows, which are very interesting because they appear a lot in nature and in a lot of different applications. And we want to do so through a variety of methods, including data fusion, data-driven methods, or reduced order modeling of flows for finding effective control strategies. We are focused in particular in impinging jets and on heat transfer, and Martin did a very nice introduction on jets. So we are talking about that also. Last year was devoted to experiments and to working on them. This last year and a half that we have remaining, we want to focus on improving our characterization of the experiments and hopefully moving to 3D measurements, for example. So our objective is to better understand the flow control in turbulent impinging jets through, for example, low-order representations, etc. And we want to focus on heat transfer. So we would like to find, for example, control laws that help us to find effective strategies to improve the heat transfer that surfaces exposed to turbulent jets experience. And we have two experiments, one passive control case, which is an impinging sweeping jet, and one active control case, which is a turbulent jet with active control. So regarding the sweeping jet that I also presented last year, a sweeping jet is a very interesting device. It is a fluidic oscillator with which you can obtain an spatially oscillating stream of air at a quasi-steady frequency. So you have certain jitter in the instantaneous periods for each oscillating cycle. And in this case, we wanted to understand the relation between the structures, the developing structures, and the heat transfer at the wall. So we have non-time-resolved Nusselt number maps at the wall, and time-resolved Nusselt number maps at the wall, and non-time-resolved PIV maps, so synchronized. And first, we wanted to reconstruct the velocity fields from the wall heat transfer measurements using the extended proper orthogonal decomposition approach, which is a linear-based method. So the two research questions that we wanted to answer were, do we have linear correlations at the wall? Do we have Reynolds analogy there between momentum and heat transfer? And second, can we reconstruct the dominant velocity dynamics based on those correlations? And the answer to that is in this paper that was recently approved for publication. But I can anticipate that we didn't find a compact correlated subspace within the first 5 temporal modes of velocity and the Nusselt number maps. And from those correlations, we are able to infer velocity from the heat transfer measurements in the EPOD framework. So here you can see on the left our reconstruction, and on the right the test snapshots from the data set. And one very interesting thing is that we do take into account the jitter in the reconstruction. So each oscillating cycle that we reconstruct has a different period, a certain variation with respect to the mean one, and other reconstructions from literature are not able to do so. So at the end, we are able to reconstruct the dominant flow dynamics from a measurement which is in a perpendicular plane, which is also very nice. So as for the second experiment in which we are working in parallel, in this case an active control strategy, we have a standard impinging jet, which is impinging onto a heated thin foil, and it is actively controlled at the exit. So we have 6 valves which are injecting mass at the exit of the nozzle to change the jet topology. So we would like to find a control strategy so that the heat transfer at the heated thin foil is improved. Each valve obviously works at a different frequency, different duty cycles, different phases. And we want to find a control law that helps us moving from the non-actuated case that you can see over there to an optimal case in which you improve both heat transfer while minimizing the mass injection. You can see, for example, the case of all valves acting at the same time at the top. It is a very nice case in terms of heat transfer, but it is very bad in terms of efficiency because you are using a lot of mass injection. So we are going to do so through genetic algorithms with an in-house hybrid genetic algorithm called HIGO, which was developed by parts of our team, Isaac Robledo, Rodrigo Castellanos, and etc. So We did that, in fact, so we performed an optimization of the problem, and we found a solution, but we are not going to focus on the optimization problem, but rather on how to interpret the results. Because typically, machine learning optimizations are black boxes, so it is difficult to interpret the results. And it is difficult, for example, to understand why a certain change in a variable leads to a very huge improvement. So from the optimization problem, we have an optimization database, which is formed by all the cases that the optimizer has been trying throughout the optimization. So we have for each case the different frequencies, duty cycles, and the results for each case. So this is a very high dimensional space of parameters, and it is difficult to interpret them. So we are going to embed all these cases through a multi-dimensional scaling, which is a machine learning tool with which you can get a low-order representation of the high-dimensional space, in which the relations that you have are based on the similarity between cases. So in this case, what we have is this 3D cloud of points. In this case, this is colored by J, which is the cost function. The lower the cost function, the better. So here, each point represents one case, and those that are close together mean that the topology originally was similar. So already we are seeing that we are able to represent that similar cases are grouped together, and the best individuals are close together, while the worst ones are placed elsewhere. Still, this is a 3D cloud of points, as I'm explaining, so it is difficult to interpret. What we can do is project this cloud of points into the dominant planes of the embedding, which are spanned by the principal directions, gamma 1, gamma 2, and gamma 3, so that we have 2D maps, which are easier to interpret. So, for example, if we project on the gamma 1, gamma 2 plane, which is at the bottom, and we color the cases by the horizontal displacement of the footprint and the cost function, we already see that we have certain correlation along gamma 1 direction for the cost function, and we have correlation along gamma 2 for the horizontal displacement of the footprint. If we project on the gamma 1, gamma 3 plane, we again have that along gamma 1, we have correlation with the cost function, but on gamma 3, we have correlation with the vertical displacement. So that means that we are decoupling the effectiveness of the heat transfer, how much we are cooling, from the spatial steering of the footprint. For example, if we move along gamma 2, we see that the footprints are becoming better in terms of cooling intensity and quality. While if we move for a fixed gamma 1, that means the same quality, and we move along gamma 2, we see that the footprints are moving towards the right. That means that both effects are decoupled. The effect of the cooling intensity is decoupled from the steering, or where the jet is pointing to. So this is very nice because by separating cooling intensity and effectiveness, we, for example, can change the intensity while not shifting the target. And this can lead to closed-loop control strategies. For example, while with changing one parameter may change, for example, the localized steering for targeting hotspots, while other parameters may influence the cooling intensity. So these are the results we are working on currently. So as for the scientific dissemination of these two lines, this is the first paper as a result of the sweeping jet experiment. We are preparing another one for the case of the impinging jet, and hopefully by the end of this year we will have 2 more contributions. This past year we were present also at 5 conferences, in Flucom, for example, or in Tokyo, and this year we are planning to be in Madrid also. And apart from that, I am also involved in other lines within our group, for example, drag reduction on road vehicles, or background-oriented slitting measurements on heated jets for also control applications. So that's pretty much everything. Thank you all, and I hope you have questions.